My name is Yanting Lin. I'm chairing this session. We have 3 invited talks and 3 contributed talks. We'll start with Professor Shiv Sethi. I'm sorry about that. Will tell us about detecting EoR in redshifted H1 emission, please.
So I first want to thank the organizers for inviting me to give this talk. And already in the morning, you have heard a couple of talks on related issue. The first talk by Tirth, and then there was a talk by Momita, and they both talked about something related to epoch of reionization. And I would focus in this talk on the problem of detection. So after a few customary slides on which I'll spend minimal time, I will go on to the problem of how you actually detect it, and that'll be my main focus. I think this slide has to be shown in an EoR talk because like this shows you a cartoon of the history of the universe, and you might have seen it quite a few times. This is Big Bang, this is recombination, and after that there is something called dark ages, of which there are many probes these days, and I'll not talk much about that. And then there is this period that commences 500 million years after the beginning of the universe roughly, and this is called the epoch of reionization. And that period, hopefully, I mean, it lasts up to when the universe is 1 billion years old, and this period is called the epoch of reionization, this transition phase of the universe in which the hydrogen is all completely neutral to a phase where the hydrogen is totally ionized. And subsequent to that, and this period is also important, and I'll say a few words about this, from 1 billion to 13 billion. During this period, H1 is actually not in the intergalactic medium, not outside of galaxies, but actually inside galaxies. There are multiple pros of this also, and Momita did discuss some of these things too. So again, when we talk about the issue of reionization, the first thing is when did it reionize, and you may have seen these plots, morning talks too, that there is Gunn-Peterson test that shows that the reionization era is probably between 5.8 and 6.2, and I'm not showing any plots regarding this. And then there is this Planck 2018 result, which shows that the epoch of reionization is, well, more like 7.6, but it has a fair error. So surely, I mean, one thing they want to emphasize in that paper is that the epoch of reionization is less than 9. The redshift is less than 9. That's an emphasis. These two maybe they're compatible, maybe they are not. But that's not what I'll try to go into. I'll not go into. One thing that one needs to note is that these probes are complementary. There is Lyman alpha absorption. This probe is about Lyman alpha absorption by H1. And this is Thomson scattering of ionized hydrogen. So one is looking at one component of the gas, the other is looking at another component of the gas. But Gunn-Peterson test, you cannot apply to any arbitrary redshift because you need a background source for it, and you don't have background sources after a certain redshift. And CMB observation, unfortunately, are more sensitive to the integrated optical depth. They are less sensitive to like the tomography and more to the integrated optical depth. So one of the direct ways to actually see this era, and it's been around for a while now, is direct detection of neutral hydrogen in emission at high redshifts. And that's the thing I'm going to be talking about. So you have neutral hydrogen, pretty much the only way you're going to look at neutral hydrogen, I'll say pretty much not the only way because there could be other ways, is possible using hyperfine 21 centimeter line. So there is 21 centimeter line, hyperfine line, and you want to look at that hyperfine line. And it is redshifted, and it comes into the frequency range of 70 to 250 megahertz. So the problem of detecting this line is a problem in low frequency radio astronomy. And that will be the main focus for the remainder of the talk. Again, I'll show you some of these plots. So this is one plot that shows you how the global H1 signal looks like. And global H1 signal, you might have thought that it looks pretty simple, that before a certain redshift there is H1, and then after that there is nothing, so there will be a sharp drop. It looks nothing like that. It's a little more complicated. This actually is something that comes from dark ages, and this happens because the matter temperature and CMB temperature are not the same. Then there is a further dip that really happens after the reionization started, and then there is a rise, and then finally the reionization ends. So there is this complicated structure of what's called the global H1 signal, and what I mean by global here is integrated over the entire sky. So this is a structure in frequency, but that's not all that there is to it, because there is inhomogeneity in addition to this frequency structure. And that inhomogeneity looks a bit like, it's an old slide, but I like it, because what it shows is that if you started at redshift of 20 and try to look for the inhomogeneity in the gas, then the density field and what you would actually observe are roughly on top of each other, but subsequent to that, the signal that you observe could be more than the signal that comes from just density perturbations. And that's important to know, that once ionization inhomogeneity set in, their strength is a little more than density perturbations, so it might be easier to detect this than just look for density perturbations that we are used to. And then once it commences, and like this is 2006, it uses some normalization when reionization ends, so it ends between 11 and 9. This is a more recent plot from one of my own work done with my student, and then you can see that there are these all complicated set of models. What has been plotted here is a single mode Fourier mode of k equal to roughly 0.1. That has been plotted as a function of redshift. That has been plotted from redshift of 30 to 10, and you can see all these class of models are possible, right? So the signal can vary from roughly 10 to the power 3 millikelvin square to, well, I mean, almost 0. So all these are possible, and there is this whole set of models which are allowed. What is very interesting in this plot, and that's why I wanted to show you, because I don't know if anybody talked about this results of edges. The edges result, which actually is a detection of H1, global H1 at redshift range between 17, 19, and 15, does give you, does say that the detected signal in fluctuating components is also quite large. You can see this model stands up on top of everything else. And I'm not going to say much about it, but if you have questions, I can discuss it later. Okay, so here is the problem of detection. What is the challenge in detecting this signal? Where is the problem? First of all, we cannot detect H1 directly by imaging, because imaging to statistical detection sensitivity, roughly if you compute actually for some idealized experiment, is the ratio of primary beam to synthesized beam square root of that. Primary beam of an experiment can be 5 degrees, synthesized beam could be a few arc minute. Divide the two, take a square root, and you know this factor is large. So if you want to detect something, might as well try to do it statistically, not through imaging, even though it might be harder from the point of view of systematics. So all the ongoing experiments are targeting statistical detection of the signal. None of them is actually trying to image it. That will happen later. So statistical detection, so MWA, that's some data that I work with, and I'll talk about MWA data in this talk later on. There is LOFAR, there is paper, there is HERA that's being planned, ongoing. Right now it hasn't started observing yet, and then there is SK1 low, which is in the future. Imaging might be possible with SK low, but not with any of these other telescopes. LOFAR, there are papers that say that maybe it's possible. So first thing, if you want to even statistically detect this signal, I did not tell you about the signal strength because I went a bit fast over those view graphs. Signal strength varies between 10 millikelvin to 100 millikelvin. It could be negative or it could be positive. Edges results suggest it could be 500 millikelvin. Now that's very large, right? But that's specific to a small redshift range. So that's problem number one. You have to integrate for hundreds of hours to get anything at all. Second, foregrounds are more than 1,000 times larger than the signal. 1,000 is just a number. I mean, it could be 10 power 4. It could be a little less also. It depends on what the signal is, and I showed you that the signal strength itself is fairly uncertain. So we cannot exactly be sure how much more but we know for sure that foregrounds are much larger than the expected signal, between 100 to 10 power 4. Now, what do we do? This is a crazy experiment, right? Somebody will think foreground larger than the signal, forget it, you can't actually detect it. Why do you even think that it is detectable? We think it is detectable because of one reason. Foregrounds are dominated by optically thin synchrotron radiation. That's what foregrounds mostly are. It's optically thin. Optically thin is important. It can't be optically thick. So optically thick, it will have frequency structure more complicated than optically thin for synchrotron radiation. Brightness temperature varies very sharply, but still in a small frequency range. It's spectrally smooth. H1 is spectrally not smooth. If you look at, you make an H1 cube, you take one map and try to correlate with the other, there is a very sharp decorrelation length in frequency space, not in foreground. Foregrounds are perfectly correlated. Can we make use of it? That's the only thing we can make use of. And that's precisely what we try to do. One is structureless in frequency, the other has very sharp structures. This allows us to want to either subtract foregrounds, and I'll say briefly how to subtract foregrounds, but my talk would focus on how you isolate them. Because the whole game is to isolate them, not to subtract them, not even tried. Then there's this problem of calibration, which is an even bigger big problem. Forget about all of this. How do you calibrate such a system? Can you actually calibrate it in reality? Answer to that, I think roughly would be maybe no. What we really require is flux phase and bandpass calibration should be better than 1 part in 10,000. You know, that's a lot. Again, when it's only a problem of isolating foregrounds, you don't really have to worry about flux and phases. Because flux error means you don't know what the flux of the source is, you have overestimated, underestimated, fine, no problem. But you know where it, and phase error means you don't know exactly where it is, you shift its position. But we can take care of that in isolation problem. Bandpass calibration is absolute necessity, even for that problem. So either all three or at least one of them is needed to one level in 10 to the power 4 to be able to solve this problem. So this is just a cartoon which actually says pretty much what I already told you. Like this is 120 megahertz. So this is a fluctuating component of the galactic foregrounds. All these 2Ks and all these are just a fluctuating component because we are comparing it with fluctuating component. Sky at 220 megahertz is much brighter than this. So galactic foregrounds 2 Kelvin, extragalactic 0.8, signal around 0.5 millikelvin, and you can see the ratios. We are talking about 1 part in 1,000. Then, if this is not enough, there could be more complication. Free emission, if it is free emission and it plays a role, that could be optically thick from compact regions, and that could create its own problems. Okay, so how do you detect this using radio interferometers? So first you identify the relevant scales in the problem and map to the parameters of the radio telescope. So the radio telescope is basically a baseline and it has a frequency width, it's a channel width. Right? That's what radio telescope is. It turns out that you can actually map this to the different Fourier components of the H1 signal. So H1 signal is actually a 3-dimensional signal, and you can match each of these baseline, which is a vector on the plane of the sky, and the frequency width, which is along your line of sight. So it's 3-dimensional Euclidean space actually, which you can map to another 3-dimensional Euclidean space that is spanned by the Fourier components of the H1 signal. So these are the three relations. That's very neat. So you take a radio telescope, you look at the sky, and you map fairly reasonably with errors. I will not talk much about that. Each of these components, Fourier mode of the H1 signal. So that is neat. It's good. How about foregrounds? What do foregrounds look like? Foreground actually, like I said, is spectrally smooth. So you can find, for instance, you have a set of point sources all over the sky, you can form its visibility. Visibility is the quantity radio astronomers actually measure. And you can define it in what's called delay space. That means you take a Fourier transform of it, take a correlation of it. And what it turns out is that foregrounds, if you have the 2-dimensional region, and I will show you those 2-dimensional regions in pictures, one corresponds to the Fourier mode on the plane of the sky, another corresponding to the Fourier mode along the line of sight. There is a neat region which is not contaminated by foregrounds. So there is this region which is actually a linear relation between the delay parameter, which is called eta, which is a Fourier component of the time, the baseline, which is u, the position of the source, and this linear relation defines what's called the wedge, and that's how it looks like. Pretty good. So let's look at this plot and try to understand what this means actually. So this is an isocontour in k parallel, which was the Fourier mode of the H1 signal. You would say, why are you plotting things which do not correspond to foregrounds? So these things do not correspond to foregrounds. These correspond to the H1 signal. We use a single space for all our description. This is k parallel, Fourier mode of the H1 on the plane of the sky, k parallel along the line of sight. And you can see this region is clean. This region is highly contaminated. You can see the level of contamination, and this is not normalized. This is not normalized, but you can see the range is roughly okay, and I'll show you data. The range is the same, right? Only it will be normalized differently. So this is called the EoR, clean EoR window it's called. This is very clean. It can be made arbitrarily clean for all practical purposes. And we can make it as clean as we wish under ideal conditions. Again, this region, this is what's called the wedge, and this just simply comes from the fact, this fact region here, that we do not actually have frequency width is finite, it's not infinite, so you have this higher harmonics that contaminate this region. So what we are looking for is isolate foregrounds. Look for signal here. That's our aim. You might ask, what would have happened if if I try to subtract, and I'll try to get to that question after this view graph. This is how the H1 signal looks like. Now this is again for a given power spectrum, and I told you there is a fair amount of uncertainty in the power spectrum. This is too much power on small scales actually, large scales, small k's. But you can see H1 signal also is dominated by exactly the region which are very contaminated, right? So, but do you have a fair number? Here the signal is large. It's maybe an order of magnitude larger than the region which is not probable through isolation technique, but this is probable. But suppose you could actually make an image, subtract all sources one by one, then this region would become available to you also. So in principle, if you can subtract sources, you are lucky. but mostly you can't. Mostly you rely on the technique of isolation. And that's going to be my focus. You cannot, but you lose out. When you try to isolate, you lose out on a part of the signal. It's very clear that this signal is not accessible to you. It's buried into foregrounds, and you can do nothing about it. Okay, so these are the different modes of detecting the EoR that there are many more in the literature. I've just listed a few of them. So for instance, imaging in real space, you just take the sky and make an image in three-dimensional, and try to subtract foreground one by one. Take a point source, calibrate it, subtract it, and then use some technique to subtract out diffuse sources. Finally, you are left with Gaussian random noise and the H1 signal buried under it. And that has been tried by LOFAR reasonably successfully, I would say, but not completely successfully, because they haven't released most of their data yet. Or you can isolate you can make an image and then use isolation in Fourier space. In fact, even this LOFAR paper uses just that technique. You can make an image and then isolate. You may not want to make an image, and that's important too. That if you have a Fourier mode, what you actually measure in radio astronomy are Fourier modes, and they have a direct relation with the H1 signal in Fourier space. So why make an image at all? You may actually obviate the need of making an image at all. So here the power spectrum is computed using some variant of delay space approach from residual visibility, and this was the original approach of paper. And this is something we have also tried in imaging array, which is MWA. MWA could image, and people have imaged using it. And the whole point is that this is also a Fourier-based technique. You never make an image. You just use, and you forward model the H1 signal. You compute visibilities, and you know when I compare or correlate to visibilities how the H1 signal might have behaved when I would have correlated it. You simply use it. And that can be done, and that is something that we have actually tried. One advantage of it is it doesn't require matrix inversion also. Noise-dominated matrix inversions is a mess, so it avoids that. And the third technique, which I'll briefly describe in the rest of the talk, is drift scan. This is something we are working on right now. That visibilities, you again take visibility, but let the sky drift now. No, you don't actually try to image the sky, let the sky drift past you. So, but if you let the sky drift, visibilities are over a region of the sky, they are correlated. And correlation of visibility in time can actually give you comparable signal to noise as compared to tracking mode. And this is something we are actually doing now with MWA data, and those are some of the things I will show you. Okay, so here is a summary of experiments I've done so far. These summaries were shown in a different way in the morning actually. So paper, this was the best limit by 1,000 hours of data. This has been retracted and revised upward by a factor of 10. That's one result. LOFAR has, just based on 13 hours of data, they have far more data than this, but the published results are only based on 13 hours of data. MWA, again, 30 hours of data, and these are the upper limits. And GMRT was the first one actually, which was mentioned by Tirth also. And this is on larger Ks actually, because GMRT doesn't have a lot of small baselines. GMRT is dominated by large baselines actually. So the value of K, the Fourier mode, is slightly larger. One thing that has to be noted here, and this is a point I would like to emphasize, is that when people talk about experiment, they normally mean more integration time mean better result, but that may not actually be true here, because somebody has integrated for 1,000 hours, given one result, somebody has integrated for 10 hours. If you actually try to compare it with theoretical noise, you may have no correspondence. So far, one thing that has not happened in this area of research is a correspondence between integration time and theoretical expectation. And that has proved to be very hard in this area of research so far. So again, I'm running out of time, so I will just, there are advantages and disadvantages of doing drift scan, and I will just go over this view graph and show you some plots that we have made recently. So this is, take 2 minutes of data, and I have plotted the same thing that I was trying to show you in view graphs, except for the fact you'll immediately notice there are these horizontal bands that have to come from the instrument. MW has missing frequency channels, and when you go into Fourier space, they create this horizontal band which is useless for us. So we lose around 30% of data just because of these horizontal bands. But it looks pretty much like what I showed you from a simulation. There is this band, there is a wedge-like structure, there is a reasonably clean region. This is our 2 minutes of integration. Let's see how it looks like after 120 minutes. From 2 minutes to 120 minutes, two things have happened, and I want to draw your attention to those things. First is that these regions have become cleaner. You see the scale has changed. The scale was close to 10 power 9. It has actually changed by a factor of 60 roughly, which was completely expected. So these regions have actually become cleaner. But actually these regions have also become cleaner, and why should that be the case? So drift scan, in principle, gives you a way to mitigate a part of the foregrounds also. It's not, we are not sure we can actually mitigate it completely. I don't think we can ever do that. But it does take out a part of the foreground also, and you can actually see that even this region is fainter. Not only that, here we expected, this is our region of interest. This is where we want to detect the signal. And so we have done this kind of noise simulations for more than 5 hours of data, and we can see the expected noise behave exactly as it should. That's result 1. But there is one more thing I'd like to draw your attention to, and this is something that people have mentioned already in the morning. Route to detecting H1 from EoR is probably not 150 megahertz. Like, one has to look at larger frequencies, and larger frequencies, for instance, if you look at H1 in emission, everybody talks about detecting H1 in emission at redshift of 10 as it's going to happen tomorrow. The highest redshift from which H1 has been detected, single object, is 0.2. This is not a high redshift, it's pretty low redshift actually. For going to higher redshift, people do what's called stacking, and I've been involved in that study. For instance, using deep to data using GMRT, and we have stacked 850 deep to galaxies and got pretty deep in doing this. So this is a technique that would come after this. At first you try to directly detect it, you can't do it, so stack. Stacking gives you pretty good, we reach pretty close to theoretical noise here actually in doing this. And you can compare the typical kind of number that you would get at 150 megahertz. After you're done with this, you cross-correlate density field with known redshifts of H1. And this has been tried by Chang et al. It's a well-known result. It was a detection actually. And after you're done all of that, you autocorrelate the H1 field. This is not yet done. When you do autocorrelation, their systematics change actually. This is much better from the point of view of systematics, not this. UGMRT will play a very important role in all of these pursuits. And we are directly involved in that. I mean, we have 500 hours of data on this, and we're going to try to do it. We'll try all these things one by one, but redshift of 1, not redshift of 10. So here I will end with this view graph. So ongoing experiments, I've put some upper limits which are still much more than where we want to be actually. And upcoming experiments will do better, of course, or so we believe. And SKLO may have the capability to go beyond statistical detection, which will be very fascinating if it ever happens. But a point I want to underline is that one needs to develop new algorithms for the detection of the signal. The usual methods of radio astronomy may not actually work for the kind of problem we are facing here. So I'll stop here. Thanks a lot.
Thank you very much. Questions?
So as you mentioned, in the stacking of the H1 signals of known galaxies, very few galaxies above 0.05 redshift are detected in H1. So where do you look, and what are the numbers of galaxies that you have?
We actually looked at deep 2 galaxies. So these are deep 2 survey, which gives you redshift between 0.7 and 1.3, 1.4 roughly. So we know the redshifts of these galaxies to a reasonable precision. Around, the 30-40 kilometers a second, we know the redshift of those, I think around 60. So spectroscopic redshifts of those galaxies are known, so we know where they are, and so we just stack them.
What's the number? How many?
850. What we did was stack 850 galaxies roughly. I mean, in 4 deep 2 fields which are observed for 12 hours each, so it's 48 hours of data, right? On which 850 galaxies were stacked. And we were expecting theoretical noise around this, we got it. So 610 field GMRT is excellent, it's very good field.
One quick question? Okay. If not, then thank Shiv.